Takže dobré ráno. Já pro české studenty a zájemce jenom upřesňuji, že následující přednáška je převážně pro zahraniční studenty a tudíž bude v anglickém jazyce. Týká se experimentálních metod a zkoušení vozidel a tématem přednášky jsou emise z mobilních zdrojů, zejména tedy výfukové emise ze spalovacích motorů. Tyto přednášky nabízíme i v českém jazyce. Na obrazovce na mne naleznete kontakt. So, good morning, dear students. I'm sorry that I don't see you here in person, and I hope to see you hopefully soon. Today's lecture will be one of the 3 lectures on vehicle emissions. It's part of experimental methods and measurement, which is part of European Masters of Automotive Engineering in the last year of Master of Science Studies here at Faculty of Mechanical Engineering at Czech Technical University in Prague. My name is Michala Vojtíšek. I am professor of construction engineering, and my specialty is fuels, combustions, emissions, and especially real-world emissions and new measurement methods for vehicle emissions, and also assessment of the impacts of new fuels and new technologies on vehicle emissions, air quality, environment, and human health. On the introductory slide, you see an example of emission test at our laboratory in Rostoky, and on the right side there is example of measurement using an instrument mounted in the cab of a heavy-duty truck. The instrument we have built ourselves. So, there will be 3 lectures. Today we will discuss pollutants from internal combustion engines. Why are they dangerous? Why are they produced, and how we can reduce them? We will overview test methods, and during next 2 weeks we will get into more advanced methods of measurement of gaseous pollutants, particulate matter, unregulated pollutants. We will also run through some calculations of air-fuel ratio, and tomorrow you were supposed to have a laboratory tour of Rostoky. Due to coronavirus, that was changed to a virtual tour, but again due to coronavirus, we are not able to film the tour of the laboratory tomorrow as planned, so we will try to film it later. So for now, I will postpone this to January 7th, to Thursday, January 7th, the normal time of your exercises. It will be streamed, it will be online, and there will be a video of the lab tour that you can watch. And during that class time, you will be able to ask questions. I'm supposed to tell you what are my office hours, but you are not allowed to enter the building, so it's pointless. So please write me an email or call me by a telephone if you have some questions, concerns, you would like to discuss something that either was in a class or was not in a class, or you are simply interested in a topic you would like to learn more about it, about our research activities. So, why do we care about vehicle emissions? Well, to me, the number 1 reason is human health. Vehicles emit their exhaust gases right in the streets. They do not have high chimneys, they are not far away from the cities, they are in our streets. And we use them. It's part of personal freedom, mobility gives us freedom to move ourselves, move goods. Mobility is associated with economic growth. And we use tremendous amount of fuel that's burned directly in a street. And outdoor air pollution, to which mobile sources, including motor vehicles, contribute to, is one of the greatest environmental hazards. It's in the top 10 causes of premature death, along with smoking, obesity, lack of exercise, diabetes, heart failures. In Europe, particulate matter in the air is responsible for something about 400,000 premature deaths per year. That number, luckily, decreases year to year. Every year it's lower, despite the vehicular traffic being steady or even in some cases increasing. But it's still very high. Now, the statistics vary. For European Union, 27 countries is about 390,000. For the 41 countries in Europe, it's about 417,000, and this is per latest European Environmental Agency Air Quality Report from the year 2020. Other pollutants of concern, nitrogen oxides, are responsible for, according to the report, 55,000 premature deaths, and ozone for just under 20,000. And compared to that, traffic accidents is only 25,000. So this is an order of magnitude difference. The difference is traffic accidents. That's a hard number. And you get to see the bodies. You know, this person has died from traffic accident. With air pollution, it's not exact number. It's a statistical estimate. It is derived by comparison of number of premature deaths in areas with better air quality, worse air quality. During the times that you have better air quality and worse air quality. It's an estimate, and very rarely, practically never, you get to point to that person is air pollution, this person is not, that person is air pollution, this person is not. It's a contributing factor. Here are some links to more statistics. Overall, it's about 0.1% of the population, about 10,000 in Czech Republic, according to World Health Organization and according to some studies. Study by Czech National Institute of Health, 7-year-old, claims 7,000 to 8,000, but not everything was reflected there. Worldwide, according to World Health Organization, it's about 7 million. So it's order of magnitude 1 out of 1,000 people in the world dies every year just because of outdoor air pollution. There are economic losses associated with it. The World Bank, in their 2016 report, estimated the economic losses of air pollution, and it varies by the region. In some regions, household particulate matter is substantial. South Asia, Sub-Saharan Africa, not as much in Europe. We don't cook on open fire, we cook on natural gas or electricity, and some people use microwave ovens for cooking. Outdoor air pollution or ambient, this one, that's about 4.8% in Europe and Central Asia. It's about half of that in North America, and it's not much higher in other countries. Maybe that means that economic wealth allows us to drive more vehicles than less wealthy regions. That's why we have higher damage. It's possible that wealthier regions produce more gross domestic product, so there is more damage. Healthcare is more expensive. We put a higher value on human health, on human lives. I don't know. And it's also an approximate number. So it's about 5% of the world gross domestic product. So we do have near zero emission engine technology that you have discussed in your other classes, including some of the heavy duty diesel engines are approaching zero emissions, at least in a laboratory. Electric vehicles have zero tailpipe emissions, and very much depends on how you produce your electricity. Same thing with hydrogen. We also have number of older vehicles on the road, and not always we use best available technology. It costs money, either during the manufacture or during the operation of the vehicle, so some people choose not to use the best available technology. And for those reasons, motor vehicles remain one of the principal sources of air pollution. Now, if you burn a kilogram of coal in a household stove, you produce much more particulate matter than if you burn 1 liter of diesel fuel. But to accelerate a fully loaded truck, 40-ton truck, to a highway speed of just under 90 kilometers per hour, well, it takes about a liter of diesel fuel. Well, that 1 kilogram of coal goes much longer way when you are heating your house. And even the houses have chimneys, and nobody is sitting on the top of your chimney breathing that air. So, why do we still have air pollution problem, and what can we do about it? Well, this is the inside of not just natural gas-powered vehicles. This is how the inside of a tailpipe of modern diesel engine should look like, and this is a California locomotive. Modern engines are equipped with diesel particle filters, which can filter the exhaust so that sometimes there are even less particles in the exhaust than there are in the ambient air. This is a look into the inside of a diesel-powered excavator in Switzerland. So, near zero emission engine technology, we have it. We need to make sure that we have it. That's why emission tests for research purposes, for legislative purposes, for purposes of making sure that everything is working well, are very important. And that's what we will discuss. So, there are some efforts to have electric vehicles and non-motorized transportation. Here in Prague, about half of the trips are done by public transit, and considerable portion of public transit uses electricity as the choice of energy source. So, if you ask me about electric mobility, well, there are trains, trams, electric buses running on overhead trolleys. There is the metro or subway, and everything works very well. But still, we rely on internal combustion engines to get us around. And in rural regions where the population density is not as high, well, public transit is not very practical. So many places rely on internal combustion engines, and that has some effects on air quality. This is a picture I have taken that's maybe some 20 years ago. We don't see that much haze in Prague anymore, but that orange color is a color of sort of the photochemical smog mixture of nitrogen dioxide and particles, and the sun or the moon gets to much larger size than it normally does, and that's because of scattering of the light on particles in the air. According to the state of California, the air pollution effects are almost comparable to second-hand smoking. So, what is being emitted? Why is it being emitted? Well, internal combustion engines today use primarily hydrocarbon fuels. The simplest one is methane, which is the principal component of natural gas. Then little larger chains are propane and butane, which together are sold as liquefied petroleum gas or LPG. Then there is the favorite fuel of many petrol heads, which is isooctane. By the way, isooctane by definition has an octane number of 100, so it's a perfect fuel for gasoline engine. And isooctane is 3-methyl pentane, 2,2,4, 3-methyl pentane. So we have metal groups 2, 2, and 4. Each carbon has four hydrogens or 4 bonds, so this is isooctane. Now, at high temperature, you burn it. It's not that you take a molecule and magically you have some products. The combustion goes piece by piece. A hydrogen is separated. Metal group is separated. The chain is broken. It is oxidized to some intermediate compound, and so on and so on. So after many steps, in the ideal case, if you have plenty of oxygen in the air and you have time, you get carbon dioxide and water. Now, I will ask our students that are also participating via Microsoft Teams to send me all the questions by chat, by text in chat, because there is about 20-second delay between the time that I speak and you hear me, and between the time you speak and I hear you. So ideally we have carbon dioxide and water. Very rarely things are that ideal. This process, if you don't have enough oxygen or if you don't have enough time, doesn't go to the completion, and you have carbon monoxide, you have hydrocarbons, which stands for a large variety of volatile organic compounds in gaseous form, which could be vapors of gasoline, but also many intermediate products. For example, formaldehyde or ethylene, which are not part of the fuel, but you have them in a hydrocarbon mix in the exhaust. All the volatile organic compounds are summed up as hydrocarbons. Not unburned hydrocarbons, just hydrocarbons. The engine doesn't burn just fuel. The engine also burns a small amount of lubricating oil that is present on cylinder walls or otherwise gets into the engine. Not much, on the order of 0.1% is the oil consumption relative to the fuel consumption. If it's very high, if your engine runs on lubricating oil, then it's time to rebuild the engine or to scrap it. Well, then you also have particulate matter, which is sometimes called soot. Well, we have to be careful about particulate matter. On diesel engines, in a diesel combustion, you have cylinder, injector, piston, and when the piston is reaching top dead center, fuel is sprayed from the injector. It atomizes, and each droplet of fuel, as it flies, it evaporates, and the vapors of the fuel mix with the air. So you have air, then you have fuel, and then roughly around here you get stoichiometric mixture of lambda 1, and that's where the combustion is actually for the most part taking place. Now, when you don't have enough air in these rich regions, it's just like pyrolysis of wood in a campfire, fireplace. When you burn wood, you drive off the volatile matter first and you get glowing chars. Well, you take all the hydrogen away. You get ethylene. When you get ethylene, that has a double bond, then you have benzene aromatic ring, 2 rings, you have naphthalene, 5 rings, you have benzoate-pyrene, which is one of the very highly carcinogenic compounds. And when you have a whole layer of these, then it's similar to graphite structure. There is not much hydrogen, and that's the basis of soot, which is elemental carbon. Now, elemental carbon by itself aggravates lungs, but it doesn't cause much of a health damage. But you might know, if you eat something that's not good, you take some active charcoal. It's not soot produced by diesel engines, it's soot produced from wood or from some other sources. And that attracts various organic compounds which become bound on the particles. So soot particles from elemental carbon also are covered with various semi-volatile organic compounds. Semi-volatile, that means they can be vapor and liquid at the same time, and usually it's a function of chemical balance. If I put a cup of, let's say, diesel fuel, well, I will have some liquid diesel fuel, but I will also have some diesel fuel vapors in the air. It depends on partial pressures of various compounds in the air. So that's particulate matter. Also, other sources of particulate matter is things that do not burn in the engine. Metals or inorganic material that is contained in the fuel or in lubricating oil, or small pieces, wear particles from the wear of piston rings, cylinder walls, piston, friction surfaces of bearings. Some of them are released directly, some of them get suspended in engine lubricating oil, and with engine lubricating oil they get into the engine. So you have some amount of metals, inorganic. We will get to particulate matter more in detail. We talked so far about hydrocarbon fuel. Now, non-hydrocarbon fuels. Hydrogen, you get a little bit of particles from engine lubricating oil, but there is no carbon. If you burn ammonia, well, same thing, you don't get much CO2. but those are rather exotic fuels. Nitromethane, for example, that's a very nice racing fuel, but it's restricted because it's dangerous. But everything else that you have in a fuel, impurities, for example, sulfur, that doesn't burn into CO2 and water. So if you have sulfur in a fuel, sulfur, metals, inorganic, sand, that doesn't burn. From sulfur you get sulfur oxides, which transform later to sulfates, to sulfuric acid. Metals are typically emitted as either metals or metal oxides or some metallic compounds. You have something else in the exhaust, and that is nitrogen oxides. Air contains about 20.9% of oxygen, but about 78% of nitrogen, and there is about 1% of argon, about 400 ppm or 0.04% of CO2, and smaller amounts of some inert gases, pollutants. Well, then you have also the water vapor in the air. So, this nitrogen I will just go get the eraser. Now I will produce some particulate matter by erasing the board, contributing to air pollution here. So nitrogen in the air at very high temperature dissociates into atomic nitrogen, and so does oxygen. And one mechanism of forming nitrogen oxides is so-called the Zeldovich mechanism, that nitrogen reacts with oxygen and you get nitrogen oxide. This mechanism is in more detail in a paper by Zeldovich, which is in a library of the Czech Academy of Sciences, and it's also described in more detail in John Haywood's textbook, Internal Combustion Engine Fundamentals. That's about what gets formed in the exhaust. So we have also nitrogen monoxide or nitric oxide or NO. Now, additional pollutants are formed in exhaust after treatment. We will discuss exhaust after treatment in more detail, but nitrogen monoxide is oxidized to NO2. Over reduction of nitrogen oxides under fuel-rich conditions produces ammonia. Some after-treatment devices, this is combustion, this is after-treatment. Some after-treatment devices produce ammonia, and some after-treatment devices working with lean burn produce nitrous oxide, N2O. Nitrogen oxide and nitrogen dioxide, NO and NO2, are summarily described as nitrogen oxides or NOx. These are not the only two nitrogen oxides, but you have nitrogen trioxide and pentoxide, N2O3, N2O5. You get dimers of nitrogen monoxide and nitrogen dioxide. All of these are not very stable and not present at high concentrations. What I also would like to mention is that if you use methane as your fuel, unburned methane is dominating your hydrocarbon emissions. And I want to make distinction here between volatile organic compounds that typically are viewed as a hazard to human health as they are, and also as a precursor to ground level or tropospheric ozone. Those are reactive organic compounds. Methane is not very reactive. It's very difficult to ignite. It's very stable. That's why it is a greenhouse gas, because it is very stable and stays in the atmosphere for quite some time. So sometimes methane is separated out, and then hydrocarbons can be divided into non-methane hydrocarbons or non-methane organic gases and methane. So that's an overview of pollutants that are problematic. Now, those are primary pollutants. Once you put something reactive in the air, it keeps reacting. So in addition to primary particles emitted by the engine, you have secondary aerosol, particles that are produced from components that are emitted, but not immediately, but after some time in the atmosphere. For example, nitrates, sulfates, organic aerosol that's nucleated. Nitrogen oxides are also one of the precursors to tropospheric or ground level ozone, which we will also discuss in greater detail. So, those particles, remember, almost pure carbon, benzene aromatic rings, large sheet of them, and when you put multiple sheets together, and nature doesn't make those like a book, it's more like a broken, crumbled, torn ball of newspapers. Well, that's about the structure of diesel soot under the electron microscope. You can see these little fringes, about half of nanometer apart. Those are layers of sheets of aromatic rings, and those form primary soot particles. And what you see in the air with your eye as a soot particle, as a black soot, those are agglomerates of primary particles. The primary particles are on the order of 10 nanometers. On the order, it means it's not 1, it's not 100, it's more 10 than 1 or more 10 than 100, but it could be 6, 8, 20, 40 nanometers. So on the order of tens of nanometers. Those are primary particles. And particles, as they float around in the air, because the gas molecules bump into them, they coagulate. The higher the concentration, the faster they coagulate, and they form agglomerates. And those agglomerates you see with your eye, because the wavelength of visible light is mid-hundreds of nanometers, 400, 500, 600 nanometers. And if the particle is much smaller than the wavelength of light, you don't see it because it doesn't interact much with the eye. I am nearsighted, if I would take off my glasses and I look outside and I wouldn't see that it's snowing. And I would know that it's snowing when an avalanche would fall down from the roof of the building. Then I would see it. So what you see with your eye are large agglomerates of soot particles. Nanoparticles you don't see. This is the typical size distribution of diesel exhaust. And you have two curves, and that depends on how you count particles. Well, there are small particles, large particles, particles of different shapes, of different level of hazard to human health, different composition, different optical properties. Well, how do you count them? The answer is lying here for a very long time. You go buy fruits and vegetables. How do you buy them? Do you say, I want 1 gram of vitamin C in apples? You can say that. You will probably not get very nice answer. You buy it by count, I want 5 apples, or by mass, I want 1 kilogram of apples. Now, if you measure particles by count, small particles will be counted if you have large number of small particles and a small number of very large particles, like a handful of poppy seeds and an orange. Well, those poppy seeds will dominate the particle number. And if I measure by mass, 1 orange will be heavier than many thousands of poppy seeds. So particles by count, most of them, they are in so-called nuclei mode, and the peak is on the order of 10 nanometers. With modern diesel engine, is more like right at 10 nanometers. This is older work by Professor David Kittleson at the University of Minnesota, one of the gurus of diesel particles and their measurement. Most of the mass in what is called accumulation mode, which are agglomerates of those primary particles. And then you have coarse mode, which is not much present in particles emitted by the engines. Coarse mode particles typically originate from mechanical processes. Not from thermal processes, but from mechanical processes. Abrasion of minerals, abrasion of tires and road surfaces, abrasion of brakes. By the way, with brakes and tires, when you start burning brakes and burning tires, then you get very high number of particles in a nuclei mode from evaporation of materials. In addition to that, you get some particles from the coarse mode. Now, contemporary engines, this is 20-year-old paper, contemporary engines by mass, maybe half of the mass or sometimes less is in accumulation mode, and about half of the mass is in very small particles in nuclei mode. Well, that's too bad for your lungs. If we think about how particles are filtered, very large particles are filtered by impaction. You get some labyrinth, and a particle is moving through a labyrinth, through your lungs or something, and you have some channels, and you have a bend. You have a bend like this, for example, and you have gases flowing, and then you have a particle which is about here. Well, inertial forces, first Newton's law, inertial forces tend for the particle to go the same direction that it was going. Aerodynamic forces act on a particle in a way the gases are flowing. Well, the larger the particle is, the larger is the ratio of particle mass, which is proportional to third power of particle diameter, then to particle surface area, which is proportional only to the second power of particle diameters. So large particles crash or impact on some surface, and very often they stay there. That's very large particles. The smaller the particle, the more is to go with the flow. Now, very small particles get deposited by diffusion. As the particles move around, because they are not that much heavier compared to molecules of air, particles move around and they stick to some surface. And once they stick to a surface, it's a very small particle. The forces of the flowing gas trying to release the particles are not very large compared to surface tension and van der Waals and other forces that are trying to keep the particle in place. So the smaller the particle, the more likely it is to deposit by diffusion. Right in the middle, there is a gap. It's around on the order of 0.1 micron or few tenths of a micron. By the way, diameter of human hair is about 40 to 100 micrometers, roughly, plus or minus. So we talk about very small particles. That's why efficiency of HEPA filters, for example, is measured at 0.3 micrometers or 300 nanometers, because that's one of the hardest sizes to filter out. Also, the reason why we are concerned about coronavirus, because it's those virus particles, when they are dry, they are on the order of 100 nanometers and they are very difficult to filter. Those very small particles do not stay in your upper nasal passages where you blow them out, but they penetrate deeper into the human lungs, and the deposition efficiency in human lung alveoli, which you have here in red, is highest for about just above 10 nanometer, 10, 20 nanometer particles, and it peaks here. Well, that's the primary particle size of diesel particles. This is why we are concerned. Now, there are emission inventories, how many particles are released into the air from motor traffic, how many particles from electric power generation. What perhaps is more relevant to human health is the contribution of different sources to particles that are on the street. And this is an experiment run by many research groups, including my favorite research group, first grade elementary school students that are looking at particle size distribution here around their school. And the highest concentration of particles were in the close proximity of major highway. And of those, highest concentrations were near the intersection, where vehicles are starting from dead stop, and you go tens of meters away and particle concentration drops. And at the school entrance is relatively low, but the hot spot around the school is the school parking lot. And if we look at the measurement done in a school parking lot, you can see that it is not a constant concentration. There are individual peaks. Well, each peak is one small cloud that originates from a motor vehicle that drove through that parking lot. And the height of that peak varies. There are tens of peaks, but only maybe about 10 of them are high enough that you can see them on a graph. And the highest one, if the graph is this high, well, the highest one is about where the roof of this lecture hall is, about 100 times the background. So the distribution of particulate matter varies in space and in time, and not all the vehicles are equal in terms of particulate matter production. There are some that produce disproportionately high particle number concentrations. The local hotspot for particles in Prague is in Spořilov neighborhood, where even during the heating season, the particle concentrations inside of a residential area picked purposely so that people use home heating during that time are in a few thousands of particles per cubic centimeter, and order of magnitude or even 2 orders of magnitude higher concentrations you get along one of the 3 motorways that surround the Spořilov neighborhood. And absolutely highest concentrations are here when heavy trucks accelerate after spending considerable time in congestion going around Prague. Well, they accelerate up the hill, and during that acceleration they produce exceptionally high numbers of particulate matter, so that you reach concentrations in the hundreds of thousands, which is about 2 orders of magnitude above what would be considered the urban background, concentrations in quiet residential urban neighborhoods with not many large sources of aerosol. Now, if we look at particle number concentrations that we measured in Spořilov and compare it with laboratory data, I just picked example from Topi Ronko's group. Topi Ronke is the head of the physics department at Tampere University in Finland, also one of the very high-level researchers in particles and diesel exhaust. So we see that particle concentrations that are measured in the air corresponds to size distributions typical for internal combustion engines. Now, not just diesel engines, gasoline engines also produce particles. They just don't produce that many soot particles, so you don't see them with your eye. They may produce less particles by mass, but most of them are semi-volatile organic compounds. So you have to ask whether more carcinogenic compounds are released by gasoline engines or by diesel engines, even though you consider older technology diesel without a particle filter. You do have to ask that question. I will not give you an ultimate answer to that because results of studies vary and individual cases vary what technology you compare to what technology, but you do have to ask that. And here is another example that road going through city of Líbeznice, there are about order of magnitude higher particle concentration than on the right side in a field. By the way, that's a rapeseed, which is rapeseed oil is a popular European feedstock for biodiesel, which is alternative fuel for diesel engines. Now, also very high concentration you get near a lawnmower. We were very surprised, but we should not be. Those are rather low technology, inexpensive engines, no electronic controls, no after treatment. Well, you have to fit within about €100 for the whole machine, so engine has to be cheap. Well, you have to ask, did a lawnmower like this produce more particles than a bus or a truck that was passing on a road? And the answer is maybe, probably, very likely, yes, it did. So if we put in place emission standards, if we put our effort, time, money into reducing vehicle emissions, then we have to very carefully look who is emitting, under what conditions, and what is the best way overall to reduce vehicle emissions. Do we increase the standards for particles for road vehicles, or do we establish particle standards for lawnmowers? Now, particle concentrations are higher near heavily traveled roads, and there are a number of studies that associate the relative risk of various ailments. This is an example of heart attack, but this is also a relatively old case with very high uncertainty. But it is not just chronic lung diseases, asthma, it is heart attacks. In the literature, there are reports on the connection of particles penetrating along olfactory nerve to the brain and possibly contributing to dementia, Alzheimer's disease. Pretty much the whole organism gets affected. Once you inhale those particles, well, some people say they have a tendency to penetrate into the bloodstream. Well, then you have them in a whole body. So that's why particle number standard was established in addition to particle mass. Because small particles do not contribute much to mass. Let's say that I drop 1 kilogram of sawdust on a floor. Well, somebody comes, tell me, you made a mess, sweep it. And then I take a 10-kilogram log and put it on a floor, and someone tells me, hey, I don't like wood on my floor. And I said, well, I just take that piece of wood and carry it away. So the contribution of small particles to mass is not very high, but there is associated health risk. So that's why we added particle number standards instead of mass. I just want to quote from the European legislation, the Directive 2008-50 on ambient air pollution, which says that there is no safe level for particulate matter in the air. Sometimes, for many pollutants, there is a safe level. If the levels are below it, well, then it's probably okay, or at least there is no sign of increased health risk. With particulate matter, you can go lower and lower and lower, and still you have some health risk. So, that's an overview. Gaseous emissions, we have carbon monoxide, which is toxic gas because it binds to hemoglobin, which delivers oxygen to your body. Well, oxygen, 2 atoms of oxygen, molecular weight of 32. It's not that much different from molecule of CO. The carbon is just a little smaller. Well, it binds, and carbon monoxide is not of any use to your body. It's a poison, and it displaces oxygen. So if you inhale it, you start being dizzy, disoriented, then you lose consciousness. You might even die if if you accumulate enough of a dose. Now, the dose that you get depends on the time that you are exposed and the concentration you are exposed to. So, when you are considering what is safe level, you have to also consider how long will I be exposed to that level. Then there are non-methane hydrocarbons, various organic gases, then we have nitrogen oxides. From greenhouse gases, we have methane, carbon dioxide, nitrous oxide, N2O. From volatile organic compounds or non-methane hydrocarbons, US EPA has identified toxic compounds like formaldehyde, acetaldehyde, benzene, acrolein, 1,3-butadiene, benzene, toluene, all 3 xylenes, and so on. Of most hazardous are probably polyaromatic hydrocarbons, especially those that are considered carcinogenic. Not all of them are. As far as nitrogen oxides, nitrogen dioxide is a brownish gas which is a lung irritant. It is because hydrolysis of nitrogen dioxide you get nitrous and nitric acid, HONO and HNO3. It attacks lung surfaces. Nitrogen dioxide also contributes to formation of secondary particulate matter and of tropospheric ozone. When nitric acid is removed from atmosphere, some of it is through formation of nitrates like ammonium nitrate, but some is in the form of acid rain. Some of the most dangerous secondary pollutants are nitrated polyaromatic hydrocarbons. Those are polyaromatic hydrocarbons that have nitrogen groups contained, and according to this paper that's mentioned here, one of the most mutagenic compounds is 3-nitrobenzanthrone, quite complicated proper chemical name, and that was found to be even in very small concentrations in diesel exhaust, and it's one of the most mutagenic compounds that has been found today. Together with 1,8-dinitropyrene, well, 1-nitropyrene with one less nitrogen group is typically found in the exhaust. This is a link to fairly useful and very detailed study by United States Environmental Protection Agency. It's a health assessment of health risk associated with nitrogen oxides, especially nitrogen dioxide. That's why we have limit on nitrogen dioxide in the air. Now, limit in the exhaust is on total nitrogen oxides, NO plus NO2. Limit in the air is on nitrogen dioxide. Why is it different? Well, nitrogen monoxide, NO, gradually oxidizes into nitrogen dioxide, NO2, in the atmosphere, so you would just assume that everything turns to NO2, so you lump sum it together. Now, in the atmosphere, we consider it separately just NO2. This is a European approach. Some other countries have limits, not for NO2, but for the sum of nitrogen oxides. So, when you compare ambient limits, for example, in a workplace, in the ambient air, Europe, United States, with nitrogen oxides, you have to read the whole thing, not just the number. Is it NO2 or is it NOx, which is the sum of NO plus NO2? The dangers are more severe than previously thought. NO2 exposure can trigger asthma attacks and lead to various ailments, mainly associated with respiratory systems. Now, another new pollutant coming at us is isochianic acid, which is formed or can be formed in diesel exhaust after treatment. it is intermediate product of hydrolysis of urea in the exhaust, but also it has been found in engines not equipped with SCR. 3 years ago, it was left as an open question. I am not aware of any large follow-up efforts. Either it is still an open question or it turned out it is not as much of a problem as previously thought. Now, tropospheric ozone. Ozone O3 is a unstable, very reactive compound. It is very reactive because it gives away its extra oxygen, leading to oxygen atom plus molecular oxygen O2. And that extra oxygen very happily oxidizes anything that comes in its way. Ozone is used as oxidant, as bleaching agents, instead of chlorine compounds during disinfection, during purification of drinking water, of water in a swimming pool, in a bleaching of paper. So you get white paper out of tree pulp, which has a little bit brownish color. Well, ozone also, ozone also damages organic material in cells. It damages tissues. It damages plants of leaves. Now, ozone also shields us from ultraviolet radiation, and there you have to distinguish where that ozone is. Ozone in the stratosphere. If you don't fly military planes, you probably don't get it high. Ozone in a stratosphere, you don't inhale it. And there it's useful. There it shields us from ultraviolet radiation. It prevents skin burns and so on. Now, at the ground level, it still may shield some ultraviolet radiation, but we also inhale it, so we don't want it at the ground level. Now, ozone is created by photodissociation of nitrogen dioxide, NO2, and what that produces nitrogen monoxide and one atom of oxygen, which reacts with molecular oxygen to form ozone. Now, that reaction, like many others, is reversible, so also ozone reacts with nitrogen monoxide to form nitrogen dioxide. Also, ozone reacts with hydrocarbons. There is OH group produced. The chemistry of ozone is quite complicated, and I can refer you to very thick textbook by John Seinfeld from California Institute of Technology and Spiros Pendis from Carnegie Mellon University in United States. Another effect that we should consider is the greenhouse effect. The Earth gets irradiated by sun. It is about 1370 watts per meter squared, out of which roughly 1 kilowatt per meter squared perpendicular to the sun radiation during clear skies and so on is received by the Earth's surface. Some of it is reflected into the space, some of it is absorbed. So Earth is absorbing visible light. The spectra is given also by the apparent surface temperature of the sun. Now, the Earth absorbs and it re-radiates some of it back into the surface. Well, in the long run, balance has to be achieved. If the Earth radiates out less than it receives, it keeps warming up. If it radiates out more, then it's cooling down. So the light that's radiated out is not visible light, it is infrared. And that's where there is a difference. Greenhouse gases such as carbon dioxide, but also water vapor, they transmit visible light. So it doesn't affect radiation we receive from the sun, but when the Earth is radiating out in infrared region, more of that infrared radiation is absorbed by carbon monoxide and other greenhouse gases in the atmosphere. So it's not radiated out. It's that energy stays in the atmosphere. As a result, the Earth has to be warming up, at least its surface. When the Earth warms up, it shifts on the black body radiation curve towards higher energies and higher intensities. So if the air warms up, it radiates more. When it radiates more, then you get a new balance. So higher concentrations of greenhouse gases in the atmosphere result in the Earth warming up until the increased radiation is in balance with the radiation that the Earth receives from the sun. This is physics. If somebody doesn't like the laws of physics, well, they are not subject to the approval of parliament and government. We might discuss what is all happening. Water also absorbs in infrared region. There is a reflectance of surfaces, like ocean absorbs more water, glaciers reflect. Ocean absorbs quite a lot of light. Glaciers and icebergs, ice cover reflects a lot of light. If you have more clouds, more light is reflected back into the space. So there is even a paradox that high sulfur fuel used in ocean-going ships results in emissions of sulfur oxide, which turn to sulfuric acid. Small droplets of sulfuric acid promote the formation of water droplets or aerosols in the air, and it increases the reflectance, so it has a cooling effect. On the other hand, black soot in the atmosphere absorbs everything, and black soot is believed to substantially contribute to climatic changes. It has a positive net warming effect. Now, you may say we had much more CO2 in the atmosphere in our history. Yes, we did. All that fossil fuel came from plant material. Well, the plant material came from carbon dioxide in the atmosphere. So there were times where CO2 concentrations were much higher and the climate was different. So the Earth was okay with that. It probably will be okay. But our civilization, the way we know it, there could be an argument that our civilization started evolving when the climate was favorable and there was abundance of food, so it was not a constant struggle for survival, but people had time to think, to invent things. Instead of 100% of our time devoted to survival, to getting food, well, the share of people that work in agriculture is decreasing. In many cases, it's less than 10% of the population directly works in agriculture and produces food. And the rest of us can do things like invent more efficient engines and higher energy density batteries for electric vehicles and more efficient photovoltaic cells and other things. So in the last 10,000 years, we had a relatively stable climate, and during that time, our civilization or different iterations of it were evolving. So we have to ask, if we change our climate by warming up the air, by warming up the earth by a little bit, do we change also the climate to the point that it will not be as favorable for our civilization? We will get less food, we will have more damages from extreme levels. By the way, have you ever thought about thermodynamics of a hurricane? Where does a hurricane get its energy? Well, there were papers published 10-15 years ago that hurricanes that get their energy from very small differences in the temperatures of the ocean, that after a passage of a hurricane, that area of the ocean has cooled down, not by much, by fraction of a degree or few degrees centigrade. So you have to ask, if you make a small change in total temperature, will you get more energy available for extreme weather events? And the answer is yes, you get more energy in extreme weather events. You get more of them, they are of higher severity, and it is all non-linear dynamic systems, very difficult to describe, to predict, but you have more energy available, and it's starting to cause problems. Here are just some examples of increasing carbon dioxide concentrations over the time. In the last 10,000 years, it was not much above 200. Now we are at 400, and it increases. Now there is a fluctuation, and that has to do with growth and decay of the plants. Now, we should make distinction about circulation of carbon and greenhouse gas emissions or excess emissions of greenhouse gases. When I breathe, I take in oxygen, I breathe out CO2. Am I emitting a greenhouse gas when I walk or ride a bicycle to work? Well, where does that carbon come from? It comes from the food that I ate. Where that came from? Well, ultimately it came from some plant that has grown. And that plant, while growing, has absorbed CO2 from the atmosphere to form carbon, which I ate, and now I'm breathing out CO2. So that's natural circulation of carbon dioxide. Carbon dioxide was absorbed by the plants, plants were eaten, and carbon dioxide is exhaled. About 97% of release of carbon dioxide into the air is part of the natural circulation. Just like here at the university we have a parking lot, and the natural circulation in a parking lot is in the morning cars come in, and in the evening cars leave. Now let's say that we would have students that would drive in some old car from Mongolia, Siberia, India. By the way, it's quite adventurous journey if you choose to do that. Well, they drive the car here. They realize they wouldn't pass the technical inspection because brakes don't work, car is rusty, and so on and so on. Well, so they just leave it here. And every semester you get few cars that just come into the parking lot but never leave. Well, those are excess cars, and pretty soon the parking lot is full of these excess cars and you have a problem. You have to deal with it. So carbon, most of it is part of natural circulation. About 3% are carbon that's extracted from fossil fuels, and CO2 is released into the air. It is not taken back. It has not been taken back a year ago. It has been taken from the atmosphere way, way back. And that's a problem. CO2 is being put into the air and no corresponding amount is taken out, just like cars accumulating in a parking lot and never leaving. So those would be considered greenhouse gas emissions, because greenhouse gas emissions are on a long term. So if I take CO2, release it, well, 1 year is nothing in climatic times. It's part of the fluctuations. So it's CO2 from fossil carbon. That's greenhouse gas emissions, and that contributes to the problem. By the way, about a third of the CO2 is dissolved into the ocean, into carbonic acid, just like CO2 dissolves in Coca-Cola, and some of it precipitates from onto the ocean floor as carbonates and so on. So with increasing CO2, we get increase in global temperature. That's also part of the measurement. Now, you may say 1 degree is nothing. Well, it's not about that 1 degree increase. It's about the fluctuations. If in this room the average is 20 degrees and it's 18 one day and 22 another day, everything is okay. Let's say someone decides, I will increase the average temperature in this room, but I will add the fluctuations. So you have 21, and one day you have 10 degrees, and another day you get 32 degrees. Well, 10 degrees would be too cold for me. I would have to put on a hat, and 32 degrees would be excessively hot. So it's not just the average, it's also about fluctuations, about the extremes. And statistics of extreme weather events follow the increase in CO2. Now, some places are better off. It's not that it's bad for everyone. Some places are better off. Some places are cooling down and not warming up. It is nonlinear dynamic systems associated with very high uncertainty, and there is ongoing debate in the scientific community. Now, where do greenhouse gases come from? In what form? Some of it is carbon dioxide. Considerable amount is methane and nitrous oxide. A lot of it is from agriculture. Methane is from cows, for example. Nitrous oxide, some of it is from agriculture, smaller amount from combustion processes, and then various halogenated organic compounds. Who is producing that? According to US statistics, electricity generation, transportation, industry, agriculture, commercial segment, and heating of homes, for example. Transportation is one of the segments. It's not a dominating one, but it's one of the principal ones. But there is a revolution in electricity generation. there is a shift to renewable energy sources, photovoltaic, wind. Photovoltaics are the fastest growing energy source due to technological advances and mainly due to decrease in price. In many places in the world, photovoltaics is cost effective. For example, opium growers in Afghanistan are switching from diesel generators to photovoltaics to power their operations and to pump water to irrigate the fields because it is more cost effective. Photovoltaics might be the cheapest energy source into the future. By the way, the International Energy Association has released their World Energy Outlook for the year 2020. And it seems like there is a much of a future for renewable electricity, mainly from photovoltaics. With transportation, well, photovoltaics on the roof of your car produces few hundred watts. That's not nearly sufficient. Electric cars, well, they are still expensive. Still the majority of vehicles are powered by internal combustion engines, and the share of renewable fuels is not very high. It's rather low. It's in units of percent. So we are facing quite major challenge with transportation. Worldwide, transport is about 1/7 of greenhouse gas emissions, but it depends on where in the world we are making this consideration. In wealthier regions, the use of transport is much higher. So, for example, in the European Union in 2015, about a third of CO2 came from transport, and about a quarter of CO2 emissions came from ground transport, which is not ships and aviation. If we look at total greenhouse gases, which includes methane and N2O, it's about 21% for ground transport and about 27% of the total transport. This number will be increasing because of the reduction in greenhouse gas emissions in other sectors. So that's an overview of emissions. What is being emitted, why is it being emitted, and the way it is associated with negative consequences. So, if I summarize, most of the vehicles are powered by internal combustion engines. Most internal combustion engines run on fossil fuel. One problem are greenhouse gas emissions, primarily of carbon dioxide, to lesser extent methane originating from natural gas-powered engines, and nitrous oxide, N2O, laughing gas, not health relevant, but very potent greenhouse gas. So those are greenhouse gases. Then we have pollutants that are relevant to human health. Number one is particulate matter. Number two is nitrogen oxides, or the total reactive compounds of nitrogen. And then down the line we have carbon monoxide, which is not as much of a problem, and various organic compounds. That's why we care about emissions, because they are very detrimental to human health, and that's associated with very high number of premature death, about 0.1% of the population, and very high economic damages, several percent, in Europe 5% of the gross domestic products. I think that's very important. I don't want you to think that emission regulations are invention of someone in Brussels or some eco-activists. Any limits on ambient air quality, on emissions of regulated compounds or of greenhouse gases, they are driven by the desire for us to live a reasonably healthy life. It's about our health, it's about our lives, it's about reasonably pleasing environment, which is very important. It's important for our lives, but also for economic activities. So those are the reasons why we measure emissions, why we limit emissions, why we try to reduce them. Next class period, we will discuss reduction of emissions by better fuels and technology. We will review formation of pollutants, biofuels, well-to-wheel analysis of biofuels, reductions through three-way catalysts in spark ignition engines, through combustion improvements, oxidation catalysts, diesel particle filters, NOx-reducing catalysts in diesel engines, SCR, diesel particle filters, lean NOx traps, and we will discuss Dieselgate. We will discuss why it's not such a good idea to cheat on emission regulations, because then as a consequence, if we don't care about our engines, then people will say, well, sorry, you cannot drive those in our cities. Now it's happening in many places in Germany. We will talk about heavy-duty engine technology that allows a city bus to have lower emissions of nitrogen oxides than many passenger cars, about upcoming emission regulations. What is the technology limit where we can push the regulations? And we will talk about emission measurements, engine dynamometers in Rostocky lab, chassis dynamometers, sampling of exhaust, measurement of locomotives, lawnmower, dilution tunnels, analytical components, and some legislation and regulation. But to start with, I wanted you to know why we care about emissions and their measurements and their regulations. So, that's it. I would like to thank you for your attention, and I will put a slide with my contact information. Now, those of you who are with us in the experimental methods class, I will switch in a minute to Teams and answer any questions live. If you are not watching this, then you will just have to email me your questions or call me. Thank you for your attention. Drive safely. Have a good day.